meeting. Okay, let's. Okay, great. So, so these first few lessons, I would say two and a bit, maybe this first week, I will introduce some of the basic concepts, okay, of combustion. So it's going to be just slides. So I'm going to give them to you on the material. You can go through them. It's really scratching the surface, okay, of a very big subject, which can be taught in different ways. I could even start talking about combustion chambers right away, okay, conversion, energy conversion devices right away. But my choice is not to do this, okay? I will introduce all of the different phenomena that you can be interested in or that are of interest, okay, in combustion. But then I'm going to go back to the basics, okay? I think a very good sort of aspect of the Italian university is that is theory-based, and I cannot stress enough, okay, how important the theory is to become solid engineers, okay? Later on in life, I think you'll understand this even more, that knowing, having a good ground, okay, basis of theory will allow you to be very flexible engineers, okay? And there's always time to actually learn about particular combustion chambers, particular injectors, okay, for example, used in liquid rocket engines or in aeronautical engines, okay? So we're going to talk about those, but we're not going to study those. We're going to study, and I'm going to tell you at the end of the slides, we're going to study the theory, okay? Starting from essentially notions of chemical equilibrium, switching to chemical kinetics, the dynamics of combustion, and then finally we're going to introduce spatial coordinates, and we're going to be studying flames, okay? Of course, there is no time to introduce phenomena that are more complex, like, for example, turbulence. However, if you are interested, that's what we do all the time, okay? Turbulent combustion in research. So this is my area of research. We do this all the time. And so if you want to continue in this, obviously you can do some thesis work, for example, okay? So I'm going to try and share my slides. There we are. Okay, can you please confirm that you're seeing?
Sì, sì, si vede.
Si vede? Okay. Not that it's of any interest, but the projector is not working well. You don't care. But if someone should come here, not going to be able to see anything. Before we start, let me just make something clear, okay, for the future, in terms of what I'm going to give you, okay, as material. I'm going to be giving you essentially my handwritten notes as time, okay, progresses. I'm going to be giving you some notes which are exactly what we're going to be doing in class. I'm going to be using a tablet, okay? So I'm going to be writing down on a tablet. It could be that if you leave me alone here in the future that I may be even doing this from home. I'm not sure. What I have to do, they're going to tell me this, okay? It's certainly much better for all of us if we're all comfortable. So if you don't want to come, then I don't see the need for me to come as well. But clearly, if you do want to come, tell me, and I'll be here, okay, in person. So I'm going to download or upload, if you want, all of the videos, the lessons on Google Classroom, and I'm going to be posting as material, okay, my notes. And I'm going to be posting other stuff as well. I mean, these slides, and as soon as as the course progresses, I'm going to be uploading all sorts of things that is necessary for the course. One thing that I'm going to do for you is, which students always tell me that is very useful, is I'm going to be posting a day-by-day kind of syllabus of what we're doing. So for every lecture, I'm going to be writing down the date, the number of the lesson or the lecture, and what we've done in that particular class. So that at the end of the course, you have a very good reference of what we've done, okay? Not all of what we do will be subject of the final exam, okay? And if it's not, I'm going to be telling you, okay? So I'm going to be specify it for you so that it's clear. Now, the exam, let me just spend a few words on the final exam. Maybe some of you may know, it's just a written exam, okay? Because there are some students that are not familiar, okay, with the sort of the Italian oral exam, so to speak, I'll just do a big written exam. But it's essentially what it is. It's an oral written exam, okay? In Italian, the Italian students will understand me. So it's just theory questions. So it's a series of questions from the theory, and I expect essentially each one of you to be able, okay, to individually essentially describe the main physical phenomena, okay, behind each of the subjects, each of the questions that I'm going to be giving you. Now, that is very important to me, okay? I don't care if you memorize things. I don't care. This is not a memory practice or exercise. This is trying to understand physics, okay? Trying to understand the physics of combustion. So these questions, if you break them down into the fundamental components of physical processes, okay, I think the course can be very easy, or can be made easy, okay? Because in effect, we're going to be talking about a limited number of physical processes that are related to thermodynamics, that are related to non-equilibrium processes like chemical kinetics, and that are related finally to transport phenomena, okay? Essentially, molecular diffusion and thermal, okay, conduction. That's all, okay? However, it's not that easy. Clearly, there is a step number 4, which is turbulence and turbulent mixing and turbulent transport. This is something that we don't have time, okay, to treat, unfortunately, because that would be, I would need another 3 credits for that. So I hope that's clear. And if you have questions on the exam, one thing, don't ask me about previous exams, okay? The truth of the matter is this. I always ask the same questions at the exam, more or less, okay? There's a permutation, but essentially there's a number of maybe 15, 20 questions that I just shuffle around. But the thing is, okay, when you sit down and for the exam, you have to know, you have to be prepared, okay, to know more or less what all that we did. You have to be able to essentially describe in your own words, in a mature, scientific, mature way, okay, what we've done in class. Okay, let me start with a few sort of relaxing slides. So this is what you've been seeing. You can see my face, right? Somewhere on the right or something. I don't know. Anyway, I'll try to make it larger. Obviously, whatever the thing is. Wait a minute. Give me a second. Modalità schermo intero. Oh. Okay, can you see?
Sì, sì, si vede tutto schermo.
Okay, great. Okay, I hope everything is working fine, so I'll start. Okay. So again, these are very sort of introductory slides, okay? So I'll start from the very beginning. You'll be surprised that I'm going to be talking about many things today, okay? So I'm going to be shifting back and forth between what combustion is and essentially where the elements are created. Well, you'll see, and a little bit of global warming as well, because so it's very, very sort of basic introduction to what combustion is. Now, first of all, let me just tell you that combustion has been a great mystery for many, many years. So much so that not long ago, I mean, if you consider 1667 as being, well, I mean, in the big game, you know, in a big context, is not very long time ago. This German alchemist formulated the first combustion theory, which was nothing short of ridiculous. It's called the phlogiston theory. And well, he essentially, in order to explain fire, what fire was, he came up with this phlogiston, which is like an element, a fire-like element, which is contained, okay, in every sort of combustible solid, for example, wood. And it would be released out of these materials when combustion would take place. Now, clearly, there's no such thing, okay? So I'm just writing it down just to tell you that we have progressed a little bit. In fact, you should use, in reference to theories of this sort, another one is, for example, the theory of the ether, okay? There's no such thing as the ether, okay? You should use the expression of Wolfgang Pauli that it's a theory that is not even wrong. So it's not even worth of considering it wrong, okay? In the sense that I will cite Pauli, it's an argument or explanation that purports to be scientific, but in fact it's based on completely invalid reasoning or premises that are completely speculative, and you cannot prove them right or wrong, okay? So you cannot discuss them in any way, okay, or in any scientific sense. You cannot build a theory, okay? So we have much better theories, okay? And I hope by the end of the course, you'll have a clearer picture of what combustion really is. I don't want to really tell you anything beforehand, okay? One thing that you may have seen in high school or maybe in the chemistry course is this sort of common or academic definition that combustion is, well, an exothermic reaction, of course. So it's hot. It releases heat, so it is related to high temperature. And it's called a redox or reduction oxidation reaction, okay? Between, and this is clearly fundamental, you need a fuel. So by fuel and oxidant, I mean two molecules, okay, that have different characteristics. The fuel is the so-called reductant. So the fuel is being oxidized, and the oxidant, okay, is being reduced. Now, as it is, this is confusing, and we're never going to touch it again in the course. I think it's a very academic definition, but still, I want to at least recall it, okay? So this is not part of the exam, okay? It's just a notion, an academic notion. So redox means that you essentially have a fuel and an oxidant, and they're being subject to two different, if you will, opposite phenomena. The fuel is being reduced, being oxidized, and it's a reductant, and the oxidizer or the oxidant is being reduced. Okay, what this means is, well, oxidation. Okay, what happens to the fuel is an increase in oxidation state. Okay, and reduction is a decrease in oxidation state. So you may have seen, for example, in a molecule like CH4, which is the simplest hydrocarbon that you can imagine. So it's one atom of carbon and four atoms of hydrogen. Okay, there is a oxidation state of each atom. Okay, within this molecule. Okay, now what that means is essentially a definition. Okay, a construct. So it's a hypothetical charge. In this case, -4. That an atom, in this case carbon, would have if all these chemical bonds that are covalent bonds or sharing of electrons, in fact, were ionic, okay? So essentially, if all these were ions, they would be, of course, H plus ions, and because the molecule is a neutral molecule, this is the carbon has an oxidation of -4, okay? If you look at what happens after the oxidation, so the reaction with oxygen, you have the production of two products here, okay? Carbon dioxide, CO2, and water. The carbon atom, you see, has passed from the methane molecule to the carbon dioxide molecule, okay? You can think of it in combustion as carbon being fixated in the fuel, okay? So you have all these carbon atoms. We'll see then when or where they come from, these carbon atoms, but essentially they are fixed, okay? For example, in a solid like wood, and then they are being released after combustion, okay, in carbon dioxide, okay? If you look at now the oxidation number, you go from -4 to +4, okay? So it's being oxidized, the fuel. On the other hand, the oxygen, which is 0 here as a oxidation number, will be clearly reduced, okay, to -2 here. Okay. Have we learned anything from this definition? I would say no. Okay, not really. I think there is much better sort of intuitive definitions. Okay. This is a little bit the picture that you're going to have most of the times, okay, stuck in your head as what really is happening, okay? So, well, here we have a chemical reaction we have between a bunch of molecules, okay? The arrow, we're going to learn what a chemical reaction is more rigorously later on, in terms of progress variables, things like that. But for the time being, it is just essentially pointing towards an energetic process, okay? From start to finish. We're not really interested in what is going on in the middle or how fast this process is. It's really between two states of equilibrium, okay? Maybe the initial state is metastable in the sense that it's less stable than the final state, okay, which is stable. By stable, of course, you will understand what I mean, but essentially, when I talk about stability between a mixture of fuel and oxidizer or these products, I mean essentially the level of energy that these molecules have. And these molecules essentially have energy because they have energy stored within their bonds, their chemical bonds. So here it is, another definition which I think is more useful. Combustion is the rearrangement of atoms and thus chemical covalent bonds between reactant and products. So Think of molecules as being Lego pieces, okay, which are stuck together, and within each sort of piece there is some energy involved, or think of them as being or energy stored in the form of potential energy, okay, in these bonds. What happens in combustion is a rearrangement of these atoms. Always remember that there is always the conservation of atoms or atomic species involved. We're not subjecting these molecules to a nuclear reaction, okay? So this is a chemical reaction. So we're conserving chemical species, okay? If you start with one atom of carbon, you'll end up with another atom of carbon. The only thing is that the carbon that before was stored in methane, okay, will be stored in CO2, okay? But you always have one atom or one mole, okay? Now, the energetic process here involves several steps. If you look, what do we have? Well, we have a starting point between here, where you have one molecule or one mole of methane, CH4, and O2. Okay, so in order for these atoms to rearrange in some other molecule, well, you first need some energy to break the bonds. So for example, the CH bonds in the fuel will be broken, and the OO bonds, okay, in the oxygen must be broken. Clearly, you need energy to do this from the outside. So it's a so-called endothermic process, okay? It requires energy from the outside. What happens then? Well, we take, for example, here, the 4 bonds, the CH bonds, okay? CH4, we've seen the molecule before, so there's 4 bonds between C and H. We need to break 4 of them, okay? And this involves it requires a certain amount of energy, okay? You can see it here. This is essentially energy in kilojoules per mole, okay? In this particular case, times 4 moles, okay? So it's the total energy needed. This will move essentially the system from a system of 0 energy to a system that is more energetic here, because clearly we have received energy from the outside. The same thing happens for the 2 molecules of oxygen. We need to break 2 double bonds here. See, they're less energetic. So if you add this amount of energy with this amount of energy, what you have now is essentially 1 atom of carbon, 4 atoms of hydrogen, and 4 atoms of oxygen. They're essentially all unbound. They're not bound between each other. They're single atoms that you have stripped outside of their initial molecules. The system, in this case, is much more energetic than it was before. See? We have essentially broken the bonds, okay, by introducing energy in the system. And the system energy goes from here to here, okay? So all atomic species will form a highly energetic system. It's called the activated complex. It's just one of the ways in which we address the fact that now these atoms are ready to be essentially reorganized in different molecules, okay? You see that there is a dashed line here. You can think of this as potential energy. So imagine a ball here, okay? In this valley, you need energy to raise its potential energy in order for this ball, okay, to go over this hump, okay? So clearly the highest energy level is up here, up on the peak of the mountain, okay? Now, this ball is now ready to find a new stable equilibrium. Now, clearly what happens is that it will fall as low as possible. So it will essentially reach the lowest possible level of potential energy, okay? So spontaneously, there is a mistake here, atoms will form new bonds in products such as CO2 and H2O, okay? Where these atoms are far more stable. So in fact, what's going to happen is we're going to form very, very energetic bonds by releasing energy, okay? So we give up some energy. This is the highest state of energy, okay? We give it out exothermically, so that's why we're producing heat, okay, in combustion, to form, for example, two bonds between CO, okay, two double bonds. You see here now, we're releasing this amount of energy. And then here we're going to form 4 single bonds between HO to form water. So we're going to go all the way down here. You see how much energy we have released, okay? And we have released more than we have put in, okay? Essentially because the net energy change, okay, in this new configuration, okay, will be obviously the the heat of reaction. So the heat that is being produced by the combustion reaction. Of course, if you think about it, the bonds in the products are stronger than in the reactants, okay? So the products have a lower potential energy. They're more stable, okay? That's why you have a lot of water and a lot of CO2 around the atmosphere, but you don't have a lot of CH4, okay? Or at least it's pretty much separate from O2. So there is a net energy release, okay? So you see that combustion can be thought of essentially this rearrangement of atoms, and it's essentially a conservation of energy, because clearly here we're not violating any conservation of energy principle. I would want to be clear with this. You have to think of this as an overall process, but if we essentially compute, okay, the difference in the reactant and products, the rest is, or energy stored in the bonds, the rest is given out as heat, okay? So the sum of this energy is always the same, okay? There is no net creation or deficit of energy. So it's very important to relate to the concept of chemical bonds, okay? This is the overall reaction, which is essentially a symbolic, okay, process where a certain number of molecules will be transformed into others, okay, at a lower energy potential, and the net effect is this release of heat, okay? Now, what are fuels? Well, usually fuels are organic, although hydrogen can be considered as a fuel. By organic, we mean the many molecules that come from organic chemistry and that have carbon atoms essentially bound to hydrogen atoms, okay? And this is what combustion 99% of the times will be concerned with, is the essentially reaction of organic molecules or so-called hydrocarbons, okay, with oxygen to form essentially CO2 and water. We always have, obviously, an exothermic reaction. Fire, okay, is one of those. The combustion of wood, for example, is a complex, let's say, phenomenon in that involves flames. Okay, flames are intermediate processes, but if you want to essentially look at the beginning and the end, okay, what we have is a certain amount of oxygen and a certain amount of wood, which is a hydrocarbon, even though it's complex hydrocarbon. At the end, you're going to have certain residues, solid residues, gases. These gases are always CO2 and water, okay, water vapor, and of course, heat, okay? So there is a trick now to understand how much heat is involved, okay? Now, one tends to think that, well, it's the energy of the bond of the fuel, okay, that is released into heat. Well, that's not really the case. In fact, the O2 double bond, okay, in the oxygen molecule is what is the ultimate cause of the exothermicity of the reaction. Why? Because O2 is a weaker bond than other, for example, double bonds or pairs of single bonds, okay? So the formation of stronger bonds, okay, in the combustion products, okay, results always in a release of energy. So if you look back at this equation, sorry, at this picture here, essentially you see that the energy contained in the fuel more or less can be considered balanced by the formation of CO2. So in this respect, energetically, we don't have a gain or a loss of energy. On the other hand, you see that the energy contained in the bonds of the oxygen atom is quite smaller than the rest. So it's not balanced by, for example, the formation of water, okay? So in fact, where we need less energy, okay, to break it, and more energy will be released in the formation of the products, in this case, water. And so there, in the balance of those two, there is always going to be an exothermic component, which essentially shows up as heat, okay? I just want to make sure, can you see everything? Because I'm talking to myself and I can't see a thing.
Sì, sì, si vede la presentazione.
Okay. So in fact, the bond energy of the fuel itself plays a minor role, okay? So there's, in some sense, they're similar or they're balanced by those of the combustion product. What is not balanced is the oxygen, okay? So there is a trick, okay, which it holds incredibly well for essentially all of more than 500 organic fuels or hydrocarbons, 500, okay, of which methane is the simplest because it has only one molecule of carbon. You can have chains, and in wood you have polymers, you have very, very long chains of carbon, okay? And this trick is the following. So we can perform a general analysis of the energy stored in the reactants and products, and which yields this result. No matter what the fuel is, so I don't care what the fuel is, the heat of combustion that is released is ultimately always around, with an error of plus or minus 3%, 418 kilojoules per mole or molecule of O2 used up in the combustion reaction. It's a very strong kind of rule. So for example, let's look at the reaction we saw up to now, the reaction of methane with oxygen giving CO2 and water. You see that we're using in this reaction, because clearly we have to balance this reaction in terms of elements. So the number of atoms on the left must be equal to the number of atoms on the right, okay? We're using 2 moles, okay, of O2. So if we take this number, magic number, we multiply it by 2, this is what the reaction, heat of reaction is, okay? This is per unit mole. You multiply now by the molecular weight, okay? And you obtain around 55.6 kilojoules per gram, okay? Now, what about propane? Well, it needs 5 molecules of oxygen. So you take this number here, you multiply by 5, and you have this amount. But more or less, okay, with respect, okay, to the molar weight of propane, okay, is always more or less the same, okay? 50 kilojoules per gram of propane, okay, being released. And you can go on and on with any sort of general hydrocarbon. If you balance this reaction, you will have X plus Y over 4. I mean, it doesn't really matter. You can do it yourself. You multiply by 418, blah, 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 and you get essentially the amount of heat that can be produced. Now, that's very important because that means that there is no magic fuel, okay? We don't have a fuel that is much more powerful than another one. More or less, when you burn, essentially the unit mass, okay, of a fuel, of a hydrocarbon fuel, you always get more or less 50 kilojoules per gram, okay, of heat being released, which has huge implications for energy devices and transportation devices, if you think about it, because that's the amount of energy that we have at our disposal, okay, to produce electricity, to propel an aircraft, or even a rocket. The most modern rockets, in fact, will work and are working with methane in its liquid form, okay? So that's a useful thing to know, okay? Which kind of breaks a little bit of the the concepts that we all have that there is some energy stored in the fuel, okay? No, it's the complex of the reaction with oxygen that is energetically imbalanced and will always yield around 400 kilojoules, okay, per mole of oxygen being reacted. Now, what's really happening? Well, we know that chemical reactions are collisions between molecules, okay? We're not really breaking anything here in terms of bonds, right? What we're really doing is having these molecules interact with one another. So these molecules are essentially bumping into each other, okay? With kinetic energy sufficiently high, so they will break. The kinetic energy involved in the collision will be sufficiently high to break the bond. Now, the truth of the matter is that there is a complex cascade of collisions, and each collision obviously will involve a chemical reaction of some sort, okay? When you have a reshuffle or rearrangement of bonds, you always have essentially a chemical reaction. That will essentially lead us from the fuel to the full oxidation, so the full production of products. So it's not just CO2 turning magically into CH4 turning magically into CO2, no. You wish. It's far more complex than that. You have a non-equilibrium process, okay, which has its own evolution speed or rate, so-called rates of reaction, with which the fuel will be oxidized into the oxidation products, which we know are CO2 and water. Okay, water in this case is not even shown because we're following in this picture here the destiny or the path, okay, of the carbon atom. And you see that it's very, very complex, okay? It's so complex that before the carbon atom is stripped, you see, of its hydrogen atoms, you see it, in this case, the first step will be losing a carbon atom from CH4 to CH3. These are very reactive intermediate compounds, which are called radical or free radicals, because they're very reactive. Why? Because they have a free electron. Okay? And so, which is very sort of ready to be reacted with something else. Okay? Before it gets stripped of all the hydrogen atoms, as I was saying, it can even get larger. Look, you see? It can even add a carbon atom. So that's in some sense, the complexity of combustion. Now, before I do anything else, let me just say that the practice that we saw until now of calculating the heat of reaction is the so-called chemical equilibrium. So it's an equilibrium kind of calculation that we're going to be doing. And we're going to be looking at the sort of configuration of least potential energy. We're not going to be using potential energy per se. We're going to be using another kind of energy called Gibbs energy. But in any case, it's an equilibrium calculation. On the other hand, when you actually consider the physical or the chemical kinetic sub-processes that will lead you from an initial state to a final state, considering the actual collisions between molecules and the rate at which these molecules collide, then you are actually looking at a non-equilibrium process and which has its own rate. So there is an element of time also involved, okay, which will tell us how fast the conversion is between products, reactants and products, okay? Generally speaking, the overall process will have its own rate. And because it's it's a sequential process, if there is in between here, very slow process or a slow reaction, then the whole reaction process will be generally as slow as the slowest process. I don't know if that makes sense, but imagine being on a highway, driving your car, okay, and all of a sudden you have a very old, tiny Cinquecento or something, or a very small car driving at 30 miles an hour. Well, clearly, maybe you can have as many Ferraris as you want on the road, but they will all go, okay, as slow or as fast as the Cinquecento, okay? Because there's only one road, okay? So it's a sequential process, so the whole thing will be, there's a bottleneck, okay? The bottleneck will be represented by the slowest process here. It's also interesting to see that you don't just oxidize CH4 into CO2, but you can have these sub-processes that actually add carbon atoms into more complex carbon molecules. Now, this is one of the reasons why burning hydrocarbons can cause pollution, okay? Not that CO2 is not a pollutant, it's a greenhouse gas, obviously, as we all know, and we will be talking about this. But these side processes, okay, or pathways, for example, in particular, this one that will tend to add molecules of carbon, okay, instead of stripping them, will cause things like soot or particulates. That black kind of smoke that you see from engines, from diesel engines, okay, is in fact the visualization of the formation of soot, which is particulate, essentially, very, very small, but on a macroscopic scale. It's not on a molecular scale anymore. The reason for the formation of this is that you have, in the chemical pathways, you have sub-processes or sub-pathways that will tend to increase the size of carbon molecules into so-called aromatic, polycyclic aromatic hydrocarbons. What that is if you add enough carbon atoms, you'll end up closing the loop, and you'll end up having pentagons, okay, of carbon or benzene kind of chains that tend to stick together. And when you have enough of them, you can actually see them, okay? And they show up as black smoke, okay? Which is very bad. This is one of the things that's bad about combustion. So I teach combustion, but in fact, I advocate the fact that it's quite bad, and we should change the way we burn things. We could avoid all of this by burning hydrogen, by the way. So that's why lately, a lot of people are talking about alternative fuels, okay? But clearly, fossil fuels that are stored on the ground, we'll see how they're stored and why there is a lot of carbon stored on the ground, it's what we're used to, right? Hydrocarbons. Now, there are other pathways. Another pollutant is nitrogen oxides. And the nitrogen comes from the air. There's a lot of nitrogen in the air. And this can be quite bad for you. Even, for example, in a malfunctioning stove at home, you can die of this gas. Okay, the X could stand for 1, 2, or 3. These are oxides. Okay, but obviously here, this is the basic product. Okay, CO2. Yeah, I've said everything. Now we've talked about the process. Now I'm going really slow, but anyway. What I'd like to do here is really take a step back. I will take even another further step back, or 2 or 3 step backs later on. But I want to put everything into context. We're talking about hydrocarbon molecules. Okay? We talked about methane, which is essentially not natural gas. And you can find it again underground. You can find crude oil underground. Essentially carbon molecules bound with hydrogen. Now, the question may arise, where do the hydrocarbon and oxygen come from? I mean, who put it there? Who put these elements there in the atmosphere to start with? And why are they in this kind of abundance? I mean, there is about 20% of oxygen by volume in the atmosphere, okay? Why so, okay? So I'd like to sort of introduce very, very briefly the concept of the carbon cycle and the way in which we're modifying this cycle through combustion, artificial combustion, okay? For the production of energy, for the industry, and for transportation, okay? Now, if you look at this picture, here you have essentially 2 atmospheres. One is a primordial atmosphere, okay? And this was an atmosphere in the so-called prebiotic age where there was no life. So at the beginning of the formation of the Earth, okay? So there was no life. You'd had essentially well, a lot of nitrogen, a lot of carbon dioxide. You had methane in the air, ammonia gases, okay? But essentially no oxygen, okay? You can see that there is no oxygen. So CO2 and CH4 in particular, CO2 is a reasonably strong greenhouse gas, but CH4 is a formidable greenhouse gas. And so you would expect to have a very hot Earth. What happens with the greenhouse gas is that the light essentially reflected back is absorbed by these molecules and then transmitted or radiated back to the surface. Okay, therefore increasing the temperature. Okay, on an average level. So that's why you sort of trap the sun's heat inside the Earth atmosphere. Now, this is before life. Now, what happened when forms of life started to appear? Essentially plants, okay? So this is what happened, essentially. There was a drastic change in the composition of the atmosphere. Why? Through photosynthesis, okay? Now, photosynthesizes organism appeared, such as plants. And what photosynthesis does is essentially this. It will take the originally present CO2 in the atmosphere, and with the input of external energy in the form of light from the sun, it will fixate, okay, the carbon atom in organic molecules. So essentially, the photosynthesis, which happens in plants, will take the CO2 from the air, some water, some energy, and will fixate, you see here, this carbon atom into glucose with the expulsion of oxygen. So that's the magic of photosynthesis. Now we have essentially organisms that actually feed on CO2. If you're ever wondering why there's so much mass, okay, stored in a plant, why plants are so huge and they can grow even if you don't feed them, well, now you know. It's because they're feeding off the carbon atom in the CO2 of the atmosphere. And they're fixing essentially this carbon atom into wood, into the material, okay, that constitutes the plants. And the bonus extra is that we get oxygen in exchange. So that's why now you have a lot of oxygen in the atmosphere, okay? Now, obviously, there's also the opposite, okay? The so-called cellular respiration, where you have essentially organic molecules that we've just formed that are essentially oxidized with the oxygen present to form CO2 and water. So this is very similar to combustion with an output of energy. So this is what happens, for example, also in human bodies, okay? And so carbon is returned eventually to the environment. But you see that now the new equilibrium is that you have a lot of plants, therefore all of those carbon atoms that you first had stored in CO2 in the atmosphere, now you have them fixed, okay, in wood, essentially, okay, or in organic material. And we have essentially replaced all of that carbon with oxygen. Now, what happens with oxygen is that now you can have, you have an oxidizer with which you can combust things and produce energy. Okay? Reason why once we've, as human beings, learned to use this conversion, energy conversion system, we have taken a great advantage from it. Now, clearly there is a drawback, as you may imagine, because obviously there is a balance that we need to respect, okay? That is, as we say, there is a biogeochemical cycle, okay, where all these carbon atoms are being exchanged among carbon reservoir. So there is some in CO2 in the atmosphere. There is a lot of carbon atoms stored in plants, okay, in biomass. There is a huge amount of carbon stored in water, okay? So there is essentially so-called tanks or reservoirs of carbon, okay, in the atmosphere, and they exchange carbon at a certain rate, a natural rate, okay? There's also a lot of carbon stored in the soil, okay? There is a fossil pool, as we know, like crude oil or natural gas. All these are reservoirs, okay? And you can express these fluxes, so essentially between, well, you can express them as arrows. They're essentially the fluxes of carbon between all of these reservoirs. And there is a natural, okay, flux, which you can express in giga or gigatons per year, okay? I won't go into the numbers here, but between the reservoirs. Now, there is a natural sort of equilibrium dynamic, okay, with all these fluxes that have settled, that have, okay, been established during millions of years. Now, what we've been doing clearly is displacing this equilibrium by introducing new fluxes. In particular, what we're doing is we're taking a lot of those fossil pool carbon atoms and burning it so that we're introducing at least 9 or 10 gigatons of carbon atoms in the form of CO2 back in the atmosphere. Okay? So this is what we've been doing essentially in the last 200-300 years. Okay, this is another depiction of the same kind of thing, where essentially you can see that before human intervention, you had essentially a balanced situation. Okay, the carbon cycle was balanced. So production of CO2 was equal to depletion of CO2. So you would have essentially a constant amount of CO2 in the atmosphere. You can see here the gigatons of carbon atoms in the atmosphere, and you can see now that there is currently in red here 165 gigatons of man-made carbon that should not be there, that we have placed there because essentially of the extra input of combustion, okay, for essentially electricity production or transport that cannot be depleted. These 165 gigatons cannot be depleted naturally, okay? There's not enough trees to do that, okay? There is something called the airborne fraction, which represents the proportion of CO2 that's been man-made, so it's called anthropogenic CO2, that actually remains in the atmosphere. So this fraction currently averages 45%, which means that essentially 50%, only half of the human-emitted CO2 can be absorbed by essentially the ecosystem, like land and the ocean. So is this bad or good? This is very bad, clearly, because what we've done is misplaced literally gigatons of carbon from their reservoirs back to the gaseous state, okay, CO2. And CO2 is a greenhouse gas, so it will trap most of the heat, okay? It will radiate it back on Earth, most of the heat from the sun, and will cause, as we know, global warming. So now we know a little bit the path, okay, of the carbon atom and how it's related to combustion. So combustion, in some sense, can also be defined as, on a massive scale, industrial scale, as the greatest disturbance of the natural carbon cycle. Now, we took a step back. Let's take 2 steps back. okay? Because we haven't answered now a fundamental question, and I think at least we should dedicate at least 10 minutes on this, because although we've seen the carbon cycle and the role of combustion and the anthropogenic CO2 in the atmosphere, we should answer a more fundamental question, which is the following: how was the element carbon created? I mean, who put it there? Why is carbon even present on Earth? Okay. And in fact, now that we're at it, we should also answer a question, and most of you will know this, but where did all of the other elements come from? Okay. The elements, let's say, that you can find in the periodic table. And so that's why we have to go really way back in time, okay? Essentially at the Big Bang. So this Big Bang is an event, okay, which is composed of a series of rapid so-called epochs, okay, in which essentially the universe expanded very rapidly, okay? When you expand something intuitively, it also cools, right? So there is a sort of a decrease of energy density. And you have to imagine here, so while the initial stages of the, let me close the door because this guy is, the initial stages of the inflation period, okay, you have a very high energy density decreasing very rapidly, okay? And so as the energy density decreased, you had the formation of the first particles. We'll see why in a second. So you form them, so in sort of a coagulation process, faster than they were annihilated, okay? In a series of events or epochs. Clearly, each particle has essentially, or the force between particles has a certain energy level. So as you cool the essentially the universe, you decrease essentially the energy density locally, and so you allow essentially these particles to come together more than being annihilated. Okay, so you first have these quark and anti-quark and electron-positron pairs, okay, that come together and annihilate very, very early on. So then after a few millionths of a second, so we're talking about almost an instantaneous thing, if the energy density now decreases below what we call now the strong nuclear force, you have essentially the first formation of nuclear nucleons, okay? So quarks become bound together in threes and form protons and neutrons, okay? Proton antiproton annihilation occurred. Now with a slight, as we know, there is a slight prevalence of mass instead of antimass or protons. So matter prevails on antimatter. And again, then as energy density decreased below the electromagnetic force, now you have electrons, which become essentially bound to the protons and neutrons to form the first, in fact, only to a proton in this case, to form the first hydrogen atom. So you see essentially the formation of the first element is really intrinsically contained, okay, within the inflation period, okay? A hydrogen atom is essentially a proton, which is a series of quarks, okay, and then an electron. So as the energy decreases, you sort of allow for these things to come together and to form this structure. And then very later on, you have under the force of gravity, which is infinitely fainter, you have the formation of sort of condensation of mass, and eventually the formation of stars, okay? Stars which are initially hydrogen stars, clearly. That's all we have, okay, in terms of elements. Very, very simple. And in stars, you have, as you know, nuclear fusion processes that essentially fuse simpler atoms into more complex ones. So in fact, all the elements are formed in stars, okay? And the stars are nuclear furnaces, essentially. What you have in stars is very interesting. You have essentially a massive action of the gravity, which kind of compresses the star, but you also have an outward expansion due to the output of energy in terms of fusion, okay? So fusion reactions. And there is a balance, okay, between the two. Now, clearly, this will continue on until you have depleted completely the fuel, the thermonuclear fuel. In this case, it would be hydrogen, okay? So hydrogen stars, very similar to our sun, okay? You have essentially a process, well, it's pretty complicated, so I'll just very, very rapidly, I mean, you don't have to know this, obviously. We have to decay this into a neutron, and then other hydrogen atoms with the neutron have form hydrogen isotopes like deuterium. They react together with another hydrogen atom to form helium. You see, now you have a more complex element here with the output of energy. And then here, these two helium will form the final helium atom. So these last two will give out energy because of the so-called mass defect. Be careful. Obviously, we're talking about nuclear reactions here. So these are not chemical reactions. As you can see here, we're not conserving elements. You see, you have, well, look at here. You have hydrogen on the left. You don't have hydrogen here on the right because you have fused the hydrogen into a new, completely new element called helium. Okay? Well, the sun has this mass. Actually, no, it has, this is the mass of hydrogen in the sun, 2 × 10⁻28 kilograms. And this is the rate at which the sun burns or fuses hydrogen. So you can roughly estimate by dividing these two numbers that the sun will last overall 10 to the 17 seconds, so about 10 billion years. But bear in mind that we've gone far more than half of that time, okay? Now, that's another interesting aspect. These are all the elements that are present in the universe. We'll get to the heavier one later on. We just talked about how hydrogen is formed, how helium is formed by the fusion of hydrogen in the stars. Now, this is the atomic number, the number of protons, okay, in each element. And as you go from, let's say, atomic number bigger than 4, okay, this is a logarithmic scale, so it's the difference between here and here is huge. You see that the abundance of other elements is far, far smaller than hydrogen and helium, okay? Not only that, but you see that it also zigzags a little bit. So it's like, it's very strange how essentially even atomic numbers are far more abundant than odd atomic numbers. That's quite strange as well. We'll try to explain that, but it's quite complicated to explain. Okay? So this is essentially the abundance of all of those elements in the universe. Okay? Well, one thing for sure is that the heavier elements are far less abundant than the lighter ones. And this has to do, obviously, with how fusion works in stars, okay? Clearly, eventually, all of the hydrogen fuel will be depleted. It will run out of fuel, okay, in the star. And now, what you have is the star will saturate with helium. But clearly now, you cannot say that the fusion will continue for helium because helium is a heavier atom. And so to fuse it, you'll need more energy. So what happens is that the star is not able to fuse anymore. So the balance between the fusion processes and the gravitational attraction will be disrupted so that the gravity now takes over and the star will essentially collapse, okay, under the pressure of gravity. Now, what happens is that the star will collapse, but the core now of the star will eventually increase its temperature until it's high enough to start fusing the next element, which is helium, okay? So that's how it works. Essentially, you deplete the hydrogen, okay? The star collapses in a smaller one, a hotter one, where now you have helium, which starts to fuse, okay? Now, clearly, when we talk about fusing, we talk about essentially overcoming the Coulomb barrier, okay? Essentially, the mutual repulsion between the nuclei of these atoms. Now, clearly, the Coulomb force is proportional to the atomic number, in fact, to the square of the atomic number. So that's why it's increasingly more difficult to fuse heavier and heavier atoms. So we saw this here, okay? And look at, I mean, we're talking about 10 to 15 order of magnitudes here in abundance, okay? So we're talking about a lot of difference between the abundances. Well, the fusion process is very complex. I won't go into any detail here, okay? You have the formation of beryllium, which now decays back to helium. You have some processes needs energy, some will let energy out. But very rarely, so very slowly, essentially, you have between beryllium decays, okay, into helium back again, you have this fusion between beryllium and helium to form, our friend carbon, okay? In fact, this excited form of carbon will decay back into helium, but very, very slowly, very rarely, you have this kind of reaction, okay? Where this isotope of carbon will eventually decay in the stable form of carbon. And this is how carbon is eventually formed, okay, in a second or third stage of a star, okay? So again, let me just say that very rarely, very slowly, this is an equivalent kind of synonym because a rare event means that overall, okay, the production of that rare event is very, very slow, okay? So carbon is formed from the fusion of helium. Bear in mind that this is the only way in which you go from helium to carbon. So from helium to heavier elements, then even heavier elements will come from the fusion of this carbon. So you see, I mean, it's a very, very slow and very rare process. So this is why heavier elements are much more rare, okay, than hydrogen. They've gone through a lot of stuff, a lot of processes in between. So essentially, this is what you have. You have small stars that can only convert hydrogen into helium. You have medium-sized stars like our sun that start from hydrogen, then helium, and then later on in life, when the hydrogen becomes depleted, you have helium being converted into carbon and oxygen, okay? Then you have massive stars, okay? Let's say 5 times the mass of the sun. And in that case, when the hydrogen becomes depleted, well, you have the conversion of helium into carbon and oxygen, followed by a series, okay, of events. For example, the fusion of carbon and oxygen into neon, sodium, magnesium, sulfur, silicon, and so on. Okay, heavier and heavier and heavier elements. Later reactions transform these elements into calcium, iron, nickel, and so on. So you see here, essentially, you have heavier and heavier elements forming in deeper and deeper and hotter shells. Okay, you cannot have very heavy elements fusing here, but they will be fusing down here. Now there is a limit, a very sort of physical or unbreakable limit to the formation of atoms, and that is iron, Fe. You cannot fuse iron to form heavier elements. However, we do have heavier elements in the universe, right? Than iron. For example, gold. Okay, gold is much heavier than iron. So there is a sequence, okay, in these massive stars. This is the sequence, okay? I won't go into any detail, but no heavier element than iron, Fe, can be fused anymore. Now I'll try to explain why. Note that in the sequence, in the actual main sequence stars, the number of protons is always increased by 2, which explains the fact that even atomic number elements are more abundant than odd atomic number elements, okay? So that's another thing that we can explain. So let's, well, forget this. Let's talk about iron. Well, iron, when iron is depleted, the star essentially, any star essentially collapses and gives rise to what are called supernova. So essentially, any star cannot produce any more, in a stable way, cannot produce any more elements. So it will collapse under the weight, essentially the force of gravity, and will produce a huge explosion, okay? As a sort of a rebound, in a way. Before the explosion, the core is obviously immensely hot with abundance of neutrons that will not coming from the fusion, okay? And so in the act of a supernova, but only in this very sort of transient explosion, not in a stable way, not for millions of years, but just in this transient, very, very fast explosion, you force essentially iron atoms to fuse into heavier and heavier elements, like, for example, gold, okay? So when you have a gold ring, know that that element was formed in a supernova. The reason why you cannot go beyond iron, well, the reason why is because, well, in fusion, you're converting binding energy, okay, into essentially heat. So iron happens to have, you see, this is the binding energy, has the greatest binding energy per nucleon among all of the elements. So what fusion does, okay, it produces, you see, by fusing elements into higher, sort of heavier elements, you produce elements with lower mass per nucleon, okay? So the mass defect here is given out as energy, okay, through the famous equation. Now, if you want to, once you get to iron and you want to fuse even further, going from left to right here in atomic number, well, then you would produce elements with higher mass per nucleon. So that means that you wouldn't have an output of energy, okay? But you need an input of energy. So imagine in a star, whenever that happens, energy is being subtracted by the overall, essentially, heat of the star. So the star starts to cool and compress and compress and compress. So it's not stable enough. It cannot, essentially, it's an endothermic reaction, so to speak. And so it cannot sustain it because eventually it will collapse on itself, okay? And so eventually you'll have a transient, well, you have an explosion, a collapse of the star. Okay? That's why we're fusing, we're doing fission, we're splitting heavier atoms because then you see we are, if this is the mass per nucleon, we're extracting energy from right to left here, okay? We're producing elements here with lower mass, okay? And the rest is essentially energy. So you see that in fusion reactors, you're going from left to right here. In fission reactors, you're going from right to left, okay? And iron is right here, split in the middle, okay? So iron is really the limit, okay? Well, we're almost over. I think it's a good, well, I'm not going to stop and we have another 5 minutes, but I usually want to waste the first lesson on talking about these things just to put in context a little bit what we're talking about here. I could stop and just talk about hydrocarbons and their combustion with oxygen, right? But I really want to put in perspective what we're talking about here. We're engineers. Obviously, combustion is important for the production or conversion of energy. Let's put it that way. So we were extracting heat from the chemical energy, and we're producing, for example, we're using this heat in a thermodynamic cycle to produce electricity. Okay, that's one thing that we've been doing for quite a number of years. But really, or we are using the same heat in a Brayton cycle, for example, to produce instead of mechanical work that can be used for electricity, we can produce a thrust, okay, in an aeronautical engine, okay, or thrust in a rocket. But really, combustion has to be put into a larger perspective, and the perspective is at least that of the carbon cycle. That there exists a cycle of the carbon atom, well, at least in the biosphere, okay, and that this carbon cycle is stable or was stable until we perturbed it through combustion. Okay, what we have done through the extraction of fossil carbon reservoir fuels is and burning it at a rate of about 10 gigatons per year of carbon atoms is displacing carbon atoms, taking those carbon atoms from solid reservoirs or liquid reservoirs and putting it back into gaseous form, bound in a carbon dioxide molecule, which happens to be a greenhouse gas. So yes, we have evolved into, let's say, a developed civilization, an advanced civilization technologically, but we've also caused an unwanted phenomenon. And that unwanted phenomenon is global warming, and that will have consequences. Which doesn't mean that we should stop burning stuff. But clearly, we should at least try to stop burning hydrocarbons. We should start thinking about burning fossil hydrocarbons. By fossil, I mean fuels that come from fossil reservoirs, come from one of the natural reservoirs. What we can do, for example, is use renewable carbon atoms. Carbon atoms that do not come, okay, from a natural reservoir, okay, but is a renewable reservoir, okay? Essentially, for example, biomass, okay, is one thing, or synthetic fuels. Fuels that, in a way, have a zero net flux of carbon atoms from solid to gas, to CO2. And you can do that, for example, by growing biological material that has absorbed the carbon atoms from the atmosphere. And then if you burn it, you're just returning it to the atmosphere. You're not transferring in bulk carbon atoms from one reservoir to another. You're not doing that. Look at how, and this, I'll finish this with this. Look at how important combustion is. Okay. Essentially, look at the world energy sources. Okay. Look at the nuclear. Okay, which is about 6%. The rest is gas, natural gas, oil, and coal. Okay. Now, this is all fossil fuels that are being burnt through combustion. Now, there is a renewable also sources of energy, wind, solar, hydro, but also renewable, combustible renewable, okay? Or renewable waste. Again, most of the renewables, okay, are fuels that need to be burnt and combusted, okay? So only this tiny amount is solar, wind, geothermal. A bigger chunk is hydro, but the rest is just stuff that we burn. So we're talking about almost 90%, okay, the world energy sources go through the process of combustion. Okay? Very economic, that's why. It's very cheap to burn things, okay? But it has huge disadvantages. So next time we're going to be looking at the production of, in a more detail, the production of pollutants and the fact that essentially we need to learn about combustion and learn as much as possible if we want to limit the damage that combustion causes to our environment, okay? So with this, I think we can close it here. Surely, if you have any questions, I'll be happy to answer them. For those who have survived, I'll probably stop the recording now.